All right. Good morning, everybody. Afternoon, wherever you're located in the country. This is Cody Cochran with MBSI WAV. First and foremost, just want to thank everybody for joining us today. Always appreciate you taking time out of your busy schedules to join us for these sessions. So thank you for that. So here at MBSI WAV, we're very proud to present this webinar along with KP Performance. Always lots to talk about when it comes to KP Performance. Lots of exciting things coming up here today. We're going to be focusing on maximizing your ROI and the best practices with high performance antennas. We're also going to get a sneak peek and I believe a Canadian exclusive announcement on the new KP line of horn antennas that are coming out in the coming months. So pretty exciting there. MBSI WAV, of course, is a proud stocking distributor of all of KP Performance's products. Just some quick housekeeping before we get started. If you have to step away or get distracted or want to share this webinar with somebody after it is over, we will be recording the session and posting it on our social media outlets, YouTube, LinkedIn, Facebook, etc. If you need a hand getting a hold of a copy, just feel free to reach out to any of us over here. We're more than happy to send out a link for you once we get it done. If you have any questions or comments during the web session, please feel free to drop them in the chat window as we move along. We are going to be addressing the questions at the end of the web session, so if you drop a question, it's not answered right away, don't sweat it. We will get to it when we get to the tail end of the session. If we happen to run out of time, if we get kind of overloaded with questions, or you think of something after the session, feel free to reach out to us, or we will follow up with you on any outstanding questions that we might not be able to get to today. If the chat window does not automatically open, there is an icon at the bottom of the Zoom window for you to open it up and type in your questions. As always, please pay attention during the web session. We will be asking a question at the end of the session. First correct answer will win a $100 Amazon gift card. So make sure you're paying attention. So again, here at MBSI WAV, we're really excited to see KP Performance not only continue to innovate on existing antenna solutions, but bringing new ones to market, as we're going to see here today. And again, just as a friendly reminder, MBSI WAV, we can help you with planning, network design, post and pre-sales support on every piece of a wireless network, including KP Performance, of course. So presenting today on behalf of KP Performance is Justin Pollock. He is a senior antenna engineer and he is based out of Edmonton, Alberta. So with that, I will pass the mic over to Justin.
Perfect, thanks Cody. If you can just let me share my screen, and we can get started here. But while we're waiting for that, yeah, I'm Justin Pollock. I'm with
sorry about that. Just bear with me here. Sorry, I'll try to get you. Sorry about that.
Okay, yeah. I'm actually a former senior antenna engineer, now I'm the product line manager for infrastructure antennas across Infinite Electronics, KP. Oh, there we go. Here we go, guys. So let's do this. Hey, Cody, which screen are you seeing? The slides or the note?
Yeah, no, we see the slides. So
okay, perfect.
We do see your notes section though, so you might need to change that.
Yeah.
Now you got her.
Okay, that should work.
Now you got her, yeah. Take her away.
Okay, good. So this is me as a younger man. I have less hair on top now. But I'm part of KP Performance and Radio Waves, and as a whole, Infinite Electronics, who is kind of the holding company that owns all these different brands. You can see KP somewhere in here, and Radio Waves, some of the brands you know, Transector, Polyphase, or Elcom, and then some of the other ones. But this is a large company, but we do have expertise in all areas of telecom. So today we're just going to talk briefly, very briefly on antenna standards. I need to set the stage with it. Then we're going to talk about total tower deployments and upgrading for capacities, different type of strategies we can do. And then also talk about maximizing our return on investment, and then some of our best practices when we're installing, and some of the things I've learned over the past years. And briefly talk about KP products, and we'll, like it was alluded to before, we're going to talk about the brand new horn antennas, which are set to release this year. But let's jump into antennas and the specs and standards. These are all different types of KP antennas, sectors, horns, parabolics. There's the KP horn there on the right. I'm just going to switch over to a laser pointer so I can grab your attention a little easier. But I think what KP is best known for, at least in the, to begin with, was the KP reflector dish. So here's one with the bicells. Atom Gen 2 on it, but we came out with the Omnis with the cases. They're well known, but let's just focus on the point of this slide, which is there's many different types of antennas, and they're all kind of can be captured by a set of properties. The most we're well known with is frequency, gain, beam width, but there's so many other ones: port isolation, front to back, pattern squint. All the mechanical properties from wind load survival, environmental survival, ingress protection, lightning protection, that it can get a little overwhelming to define them. I can tell you it takes a long time to put together a data sheet, especially when you have a lot of unique characteristics. But in any case, what is the most important? It's gain. Gain is what we see in the field. It's what gives us our signal strength. And gain, it's really just an absolute measure of power. And it's got to be referenced to something. So gain is always referenced to an isotropic pattern which radiates equally in all directions, and that's called 0 dBi. Now, gain is not a quantity that's defined by itself. It's actually defined with respect to a quantity called directivity, which is really how focused we are at pushing power in one direction. And directivity comes from the antenna shape and its design, and it's really what drives the power in one direction. But once you start taking into account some realistic things such as material loss, return loss, other sources of losses, power can be stored in the near field of an antenna and doesn't radiate far field, then we start to talk about gain. Gain is related to directivity through efficiency. Efficiency is always less than 1, so that means the gain is always going to be less than directivity. And so gain is what we see in the field, but really a lot of the time directivity is what we see on a data sheet, which is kind of weird because it's not something you'd actually see in a field test, but it's something that's reported on the data sheet because it makes the antenna look better. So we always mention this as a caveat when you're looking and comparing data sheets, is that you have to have the correct definition of gain on the data sheet. And gain, it's an IEEE standard definition. It's measured with a calibrated horn. And then but sometimes you do see directivity instead, and they won't call it directivity. Sometimes they'll say directive gain, computed gain, or they'll just say gain. But if you see something that's a lot higher than what you see on average across everyone else's data sheets, you might be kind of questioning how they're calculating that gain value. There's some theory to calculate gain just back of the hand based off the antenna size. So bigger antennas have higher gain. That's pretty standard. Or antennas with narrower beam widths have higher gain. But these are things you could just do for a sanity check. Now I'm rushing through this. This is a NIST calibrated horn. Front to back is another important one. You could define the front to back, which is the ratio of power moving forward and backwards, as just 1 point, 180 degrees. Well, that's a useless definition. I want to care about the front to back if I have two sectors that are actually back to back and I want to share channels on them. So really you should use this definition, which takes in this whole arc plus or minus 30 degrees around 180. And that way you actually have a realistic definition. Of course, it's going to make it look worse, but it's more realistic. Same thing with cross pole. Rushing through this, but this is, I've done this many times, these two slides, so I'm rushing it. But cross pole is a ratio of how much power, it's a ratio of your undesired polarization over your desired polarization. So you don't want to receive your cross pole. That's your radiating H, you don't want to receive V. You're radiating plus 45, you don't want to receive minus 45. So, of course, an antenna is never perfectly polarized or polarization parity. So it has some cross-pol component, and we measure that through this cross-polarization, cross-pol discrimination, XPD, XPIC, you name it, that's the same definition. But what it's defined as is a lot of the time just at 0 degrees. But I'm using this sector over a sector, over its beam width. So I really care about the cross-pol over this whole range of arcs here. It's a 65-degree sector. So I'm going to actually report on our data sheets the max cross-polarization ratio across that whole sector. And that's a more realistic thing. This is actually a pretty good cross-pol level. I've seen it dip all the way down to 8, and people MIMO's performance is still working great. So it just goes to show that the definitions you have in defining your parameters go a long way in determining what value you put in for that parameter. This is another setup slide here. It's just talking about how is a sector constructed. Really, a sector is a bunch of elements. It could be patch elements, microstrip patches. This is a dual stacked, air suspended, all aluminum patch. I probably messed up the name there, but anyway, it's a bunch of elements, and you stack them vertically. And by stacking them vertically, you actually decrease the elevation beam width. So you go from 1 to 2, it cuts the elevation beam width almost by half. And you keep doubling it, keeps on cutting it by half. And what does that do? Well, it increases the gain by 3 dB, about maximum theoretically. You end up getting a little bit less gain because your efficiency drops because you have some feed networks in there. Like imagine just some metal traces to connect everything together, and as a wave propagates along metal, it incurs loss, so you lose efficiency. But this is the basic principle. Sector is 8 elements or more, usually 8, sometimes up to 16 for a 90-degree sector. And that's how you kind of get these narrow beam widths and high gains is by stacking these patches. Now, why I showed you this is I'm going to show you what is the actual difference between a sector antenna and a horn antenna. Well, right off the bat, one thing you can know that is one of the main differences is the size. A sector is massive. It doesn't have to be massive, but this is a bigger one right here. It's also 4 ports, so it's a bad comparison, I would say. But a sector is usually long and rectangular, and a horn is typically circular. We've seen the elliptical ones. I'm going to briefly talk about why the elliptical ones are pretty much just sectors. But a sector antenna, it has a narrow elevation beam width and a wide azimuth beam width. The horn antenna has a equal azimuth and elevation beam width because it has a circular symmetric aperture. So what does that mean is that a sector antenna, because it has a narrow elevation, has a higher gain than a horn. It just doesn't matter if they have the same azimuth beam width and the horn is circular, the sector will always have higher gain because it has that narrower elevation. Now that's kind of this top level superficial differences between it, but one of the main, I think, something that throws people off a little bit is how beam width is defined. So for a sector antenna, a beam width is always your 3 dB roll off. So look at this outer dashed blue circle where it intersects our patterns. That is the 3 dB beam width. So that's this yellow arc here. And that means that half the power is contained within this yellow. But now let's go back to a horn. A horn antenna is actually measured, or its beam width is defined with respect to a 6 dB roll off. So 6 dB beam width is actually how much power is within 1/4, or how many span of angles where at least 1/4 of the power is attained in. So you can see here that you end up getting a significant drop off with this definition. So even though this horn, let's say it says it's a 60-degree beam width, really if you define it with the same definition as the horn, as the sector, for a 3 dB beam width, you can see it's actually about a 45 or something. So you're going to end up seeing less coverage or more signal drop on the edges of this horn as opposed to a sector. Now, very top level sectors and horns, you can compare them, like I said, the sector. So I'm comparing here a 45-degree sector to a 40-degree horn and a 60-degree horn. And you can see that the sector beats the gain. This is the raw gain measurement right here on the right-hand side. And then here on the left-hand side, we're normalized to 0 dB. And let's just focus on the right side. So you see the gain is much higher for the sector. That makes sense, what I just said before. But both compared to a 60-degree and a 40-degree horn. Now, like I said, if you want an apples-to-apples comparison, if we look at the 3 dB beam width, this sector is actually more comparable to a 60-degree horn in terms of beam width. At the same time, we see with the gain increase is significant at the center of the sector, so right where it's pointing, plus also at the edges of it. So it's a 70 dB increase over the horn, equivalent horn, and also another 7 dB increase at the edges of the sector. Now, comparing patterns, because we know horns are all about side lobes. And by the way, I'm not talking down horns because we're going to sell horns, but I'm saying there's a use case for each one of them, and we have to be able to compare the differences and know when to use one versus the other. So here we see that if we look at the raw comparison of the patterns, the sector actually has very similar patterns to the 60-degree horn, which is the true comparative here. But once you start comparing it to the 40-degree horn, the side lobes of that 40-degree horn, of course, are naturally lower because it has a narrower beam width. So that it just kind of to show you that the definition can kind of play a big trick in what you're comparing apples to apples to. So a 45-degree horn, you'd be hard-pressed to compare it fairly to a 45-degree sector to a 40-degree horn. Now, moving on, so this is what kind of what I was talking about is the use case here. So here we're comparing a 40-degree horn, 60-degree horn, and then a 45-degree sector. And we can see the 45-degree sector gets out really far. So I would say for 95% of application, a sector is going to be much better for you when you're doing long distances, rural areas where you're trying to pick up a lot of clients over a sparsely populated area. But the horn does pretty good when you want to pick up lots of people in a small distance, maybe within 3-5 miles or so. So it's all about the use cases and where you want to use that horn. Of course, haven't even talked about noise yet, but noise plays a big figure in which one you're going to be using. So next slide. There we go. So here's the horn antennas that we're releasing. So we're starting off here with a 30-degree, 45-degree, and 60-degree horn. This is reference to the 6 dB beam width. These horns, they're based off of scalar horn technology, symmetric scalar horn technology, but they make use of our quick connect adapter and technology, and also they're well constructed. So these are actually our engineering sample units. The photographer flipped the N-type connector. It should be pointing downwards. But in any case, well constructed. I'm not going to have, I don't think, any issues of these being damaged, radomes falling off, because we use a thicker radome to avoid that type of issue, or hail and damage. But this is just wanted to pause, take a look at these. Of course, these are sample units, so this label here is not going to be on the final unit, and some might be some fine finishing touches, make the colors match and everything, but this is kind of where it will look at the end of the day. Now, these are just some renderings that I did, but here's just the comparison of the part numbers, the beam widths, the 3 dB, the 6 dB beam width, and the gains that we're getting front to back. These have excellent front-to-back performance. We kind of went and looked what's on the market, and we tried to do better. So we beat a lot of our competition in the front-to-back by some frequencies up to 5 dB, but typically 2 to 3 dB. The gain is marginally higher. I mean, you can't do much with gain, but we did improve the efficiency of our antennas such that they're very highly efficient, and our gain closely matches directivity. The patterns are just awesome. I'll show you something in a little bit here, but we spent a long time optimizing these patterns. It's a different design than what's on the market right now. And of course, when I say on the market, I'm trying to avoid names here. And that different design, it actually increased our cost a little bit. We'll live with it. And it just results in a better, more uniform pattern with better side lobes and better front to back across the entire frequency range. So here we're just showing, the maximum amount of horns you can have if you have, let's see, 1, 2, 3, three channels available for a 30-degree, and then the 45 and the 60. So you can do a lot with these horns. You can get a lot for co-location on a tower, get a lot of clients just on maybe 5, 6, 7, 8, 9, 12, or 18 horns. So this is kind of where I love to look at here, and it just shows how long we spent designing these antennas. Let's just look up here. These are some fancy graphs that I pulled out of CST. It's a RF propagation software, and I'm just showing here the raw pattern strength from 0 to 40 dB. So anything below 40 dB kind of gets cut off. It doesn't get a color. But you can see here that the signal is very focused forward, and then it dies off at these larger angles. So this is the 30 degree. And you can see that there's nothing going backwards past 40 dB. Of course, this is simulation. Measurement's a little bit different, and we'll look at the measurements here. But it's just very highly focused. You're going to be doing a good job getting rid of noise in your area, mitigating it. Pretty much, I would say horns are a spatial filter. So you have, filters, inline filters for your RF path, but this is a filter which works in space, where it rejects power outside of where you want to capture it, and it does a pretty good job at it. Now, here, this is actually raw measurement results. I don't know if you guys could tell. You can get really close to your screen, but I'm actually plotting the raw measurement azimuth patterns at all frequencies. So this is from 4.9 to 6.4. And it's hard to tell, but that's why the reason this line is so thick is it's just overlapping. There's barely any difference between the pattern as you change the frequency. Like I said, we spent a long time making this happen. And it was quite an effort, but we're very proud of that achievement. 60 degree, sorry, this is supposed to be 45 and 60, and I was supposed to update that. But this is the 45 degree, little bit of difference, but it's not that bad. I mean, at low 4.9 gigahertz, that happens. And then here's the 60 degree, it's very similar in that case. Now, another very nice feature here is we have excellent VSWR across the entire band. So this is VSWR for both ports. 1.7 is great across the entire band. Typically, it's less than 1.5. So now the port isolation is another big one. Typically, we're at 30 at the high part of the band. Here, we're at 22. This is an excellent result. There is no horn product on the market which has this port isolation. The port isolation for the competitors' products are typically in the 10 to 20 dB range. It's maybe a little bit better than 20 at some frequencies, but I've seen it drop really low at some, especially at the high part of the band. And that's just the way it's constructed. We use a waveguide launcher with connectors and pins, where some of our competition are using this PCB launcher for the waveguide, and it's inherently has lower port isolation. So why is port isolation important? Because it gets you MIMO performance. And right now, the port isolation may be okay, when you're at 10 to 20 dB, but once the modulation gets more advanced, we start to go to higher modulation rates, that port isolation needs to come up in order to avoid bit error rates increasing. So here's just some more pictures, but I'm actually here focusing on our adapters. So we have our N-type adapters. We have one for the Prism station, the ISO station. We have the Mimosa C5C. We just finished the one for the EPMP 2000. This one's being tooled up now. So these all are going to be ready for release when the horns are. My hope is we can get these ones ready right after, or if I'm lucky at the same time. We're working on the Ubiquity Prism Station 5AC Gen 2, and then the EPMP 1000 and 3000L and Force 300 CSM. The reason we're doing all these is these are also used on our parabolic antennas. So you're going to be able to switch these adapters between the KP parabolics and the KP horns, and then maybe some other products in the future too, if we're lucky. So this is the adapters we have planned. We do have more kind of on our horizon as radios get released, and also looking at some of the more legacy radios too. Unfortunately, adapters they're kind of expensive pieces to tool up, so we're very careful in which ones we're picking. Just want to focus here on the mechanical design because we got to get into the fun start here. But fine tilt markings here to help you tilt everything. You could go and mount two of them side by side like this. Let's say you want to do some 4x4 with a 3000. And then I think I have, oh goodness, this is a video. Let's see if this works here. just show how the quick connect adapter works here. So you can actually, one thing I didn't say is you can rotate the polarization to between H and V and 45 slant. So this is going to be compatible with any CPE radio. Doesn't matter what polarization it wants, just by doing this simple rotation here. I think I show it right here. There we go. So really excited, like I said, about these products, well constructed. But now let's kind of get into, with those horns, we can now do total tower deployments. So what do I mean by that? I mean, you can come to KP and you can get a parabolic, you can get a sector, you can get a horn antenna, heck, you can get Yagis, flat panels, whatever you want, omnis. But we're able to support you in whatever type of application you need for the horn antenna. So here I'm just showing, our 2-foot dish and then a couple horns and then our KP dual band sector. And I'm going to show you a use case of these type of applications. So let's say, you're setting up in a new area, or you're expanding somewhere, you're replacing equipment. You say, okay, well, first thing I want to do is I got a lot of clients that I brought on, and I need to pick them all up right around this town here. So I'm going to put up 4 sectors. So you go put up 4 of our dual band sectors because you said, hey, these guys all want the highest speed possible. There's enough people to justify putting, two 4x4 radios on here, on each one of them, one for 3 gig, one for 5 gig, and then arranging them like this. And then these different colors here signify which channel you're on. So here we're just focusing on 5 gig, and here I'm just showing all the available channel space. So we say, well, we want to maximize, we want to reach far out, so we're going to be in Uni 3 or Uni 1. Let's go to Uni 3, 1 watt max power, and then put it on these 2 channels right here, 40 megahertz channels. And you're like, wow, this is great. I'm doing great. But you know what? I'm actually starting to pick up more people in town. And also these people in town, they don't get the best signal strength because I have these sectors pointed all the way out, not down tilted. So what I actually want to do is I think I'm going to put up some horns. So at first you go put up your first horn and you say, well, I'm not going to get too many people on a horn, so I'll just do 20 megahertz channels to start out with. And then this is a 30 degree that I'm showing. And then now you said, well, now I want to get this road right here. So you expand it, you start using this extra channel right here, channel 40. Now, then you got a bigger area you want to do. So you say, well, I'm going to put a 40 degree in here because the density of people is not as much, and I want to get a little bit more coverage here. A couple residential zones in that region. So you go and add another channel, and you got that next horn. Now you're like, now you think, well, I got one more channel here for 20 megahertz, but I'm pretty sure I'd be able to put up another horn without interfering with my first one. So now you start to reuse channels. And so you're back on the channel 1, and now you're just going around. You keep reusing channels, keep reusing. And then at the end of the day, you don't care about people over here. Let's say that they're served fine by this sector. And you have this type of coverage map. This is, of course, ideal. We're not showing any blockage or anything. But in any case, they're like, wow, now I'm really serving these customers. I'm maximizing my available channel space. You may be asking, why aren't you using Uni 2? And what a lot of the reasons are this silly weather radar band. It's very, you got to be careful working around. Another one is the lower power. So it's only 1/4 watt instead of 1 watt. So you're not going to get the same signal strength. Maybe you'd end up dropping down a modulation rate doing that. So in my opinion, you want to avoid it and only use it if you have to. But you say, well, I don't want to go up to 40 megahertz channels on the horn. So this is what I do. I'm dropping down here. Now I'm using all of Uni 1, but now I got to put one of these horns here into Uni 2, so it's got the lower power. But it's okay because you'd be very careful how you choose it and make sure that this horn that you choose has very good signal strength across the board, and maybe you're trying to only pick up people close to the tower. Now the other thing you could do, of course, you go up to 80 megahertz channels. Now you're really using all of the channel space available. Of course, you got to find a radio which supports this, but in any case, this is maximizing the all available channel space for this band, and we're using four sectors and 1, 2, 3, 4, 5, 6 horns here. So I just want to show one more example here. This is using KP sectors. Here I actually have some blockage stuff going on in the RF propagation map, and actually taking into account land terrain a little bit more. But in any case, we have 6 sectors using a channel reuse 3. So it's ABC, ABC. We're on these 3 channels here. And this works great. We have a lot of people doing this already in the field, and they don't have any interference issues with this. Is our ProLine 65-degree sector. We also have our standard line version too, but this is an ideal scenario if you want to put 6 sectors around the tower, and how do you reuse those frequencies. Now, conversely, you could do this with the horn instead, and ignore this tight circle. It's just because I limited my propagation calculation zone. But you could do, however many this is, this looks like 12 or something. 12 horns around the tower, sharing 3 channels. Because of the tight side lobes and great front to back of these horns, you're able to reuse the frequencies a lot more densely spaced at a sector. So you only have to end up using 3 channels to do this whole area here, and you can pick up a ton of clients here. This is obviously not the best area to do it in. I mean, it looks pretty sparsely populated, but imagine you're doing this in a suburban environment. This will work great. Now, so that's how you do your frequency reuse, and so I got a little bit of time left, and we only have about 3 or 4 more heavy slides to go through. But how do you maximize the performance of your subscriber side or your CPE side? A lot of that has to do with the antenna that you're choosing. Now, let's say you're working with one integrated CPE, and you're getting fairly poor signal strength, or you're just at the threshold where you're dropping off, or at the same time you're at the lowest modulation rate. You said, well, I want to invest a little bit more in the CPE to get up to the next modulation rate that I can charge people more. So you start working through the math, and you say, well, if I upgrade to a 2-foot dish, and you go into your RF propagation study software, you say, well, I invest maybe $50 per client additional, but then at the same time I'm going to be charging them an extra $75 as opposed to $50 or $100. So your annual and monthly revenue will increase significantly. So here's a chart showing signal strength, download and upload speeds for these clients using just a small dish, 1-foot dish, or an integrated CPE with 24 to 23 dBi gauge. But then you upgrade to our 2-foot KP dish, 29 dB gauge, and all of a sudden you're increasing your download and upload speeds, and now you can charge them a little bit more. So now you're charging them $525. This chart here just shows the changing of the modulation speeds. So before, using the integrated 23 dBi, you got someone all the way down at MIMO-A times 1 QPSK, and then going up to here, this is probably someone closer by, they're at times 2 QPSK MIMO-B. But now, using the 2-foot dish, you can get all your clients to at least this modulation rate, plus you get a few more clients here on 16 QAM MIMO-B. So this is, you're able to charge these clients, I think these are the 100 DL speeds, increase your monthly rate and your annual revenue, and get that money back right away, and, within 2 months, just for this simple example here. Now, this is actually real data that I pulled from Link Planner, so it's not something I pulled out of my hat. I went in Link Planner and did this, and then these data rates, I mean, you can set that yourself, but this is pretty much market standard for at least some markets. I know some are very much more competitive. But in any case, this is just goes to show that we shouldn't just be using the cheapest solution we can. Even though it's cheap at CapEx, you're going to be limiting yourself of what you can charge in the future. It's worth it to do that little bit more investment up front if you have the money, if you have the funding, maybe you got your cap funding, and just bite the bullet at the start. And as long as you apply a dependable antenna, you don't have to go and touch it again, you're going to get that investment back right away. Now, microwave links is another way we can maximize performance. I mean, it's very straightforward, right? We can use an integrated panel. So this is a Cambium PTP 670 with a smaller gain, and then we get an IP throughput, maybe 150 megabits per second. It costs about $2,600. But then you said, well, you know what? I'm not happy with that. I want to upgrade. So you can go up to a 2-foot dish or KP 2-foot dish. And then all of a sudden, you only have to actually pay an extra $100 to do that, but you get a much better aggregate throughput. And plus, you know, you have the KP product, which we stand by. Another thing I'd like to note is that going to the 2-foot dish has very good side lobe levels over an integrated panel. So the panel will have side lobes around 30 dB, where the 2-foot dish, the side lobes go down to 40 dB. So you're actually going to end up increasing not only your raw signal strength, but also reducing your noise floor by doing this. Now we can keep going. We can go to a 3-foot dish. So as I said, Infinite owns radio waves, so this is a radio wave part number, but this is a 3-foot dish at the same frequency. Gain goes up. Your modulation actually starts tapering off. Now it only goes to 409. I'm sorry, the throughput only goes to 409, and you end up spending an extra, as opposed to the first one, it's like $1,200 bucks. But let's say you actually needed that speed, so you're doing it this way. It's justified doing that extra $1,200 spend up front. Now, another added benefit, like I said, is the side lobes go even further down. So you can do the same with the 4-foot dish. Things start tapering off. Now we're at 421 IP throughput. By the way, this data is all through Link Planner. That's where I grab it from, and the costs are actually market costs. But you can see now that going from the integrated to a 4-foot dish, it's a significant investment, but sometimes you have to do it, and maybe you don't see it here in the aggregate throughput, but you actually start to see the benefit in the side lobes. So if you have some radiation or some RF noise, and you know it's coming from some weird angle, maybe 75 degrees, I'll say 80 degrees right here, you say, well, the 2-foot dish is only going to give me 42 dB of isolation or noise reduction. But if I go up to the 4-foot dish, I'm going to get 48, and that's just enough to get me over the limit where I'm going to start seeing the performance I want. So these are the type of decisions or questions that I start to ask when I'm deciding between different sizes of dishes. Where's the noise coming from? What noise level do you need to be above? What's your receive signal strength? And also going into a nice tool like Link Planner or pretty much any RF propagation tool, which allows you to get this data together to help you make informed decisions. We shouldn't be making it off the fly, off the cuff. Oh, it worked in this area, it's going to work in this other area. It never works in the same area, different areas the same way. So it's always good to do your research and due diligence here before we invest this money. Now, this is a very confusing topic for me, and I'm still confused on is how far to separate our antennas. There's no one rule, unfortunately, and it depends a lot of different things. So your frequency, your gain, patterns, polarization, what type of antenna it is, your environment, humidity plays a role, radio power, and sensitivity. I'm sure there's way more, but let me just kind of break it down what we're trying to do here. So antenna has 3 different regions in it. It's got its reactive region, it's got its near field region, and a far field region. The reactive region there's a lot of, it's called reactive energy, pretty much imaginary energy, we like to say, that stays stored in the near field, and you want to avoid as much as you can being in that zone. You put your hand in front of antenna, it changes its VSWR. So in the reactive zone, if you have some object near it, there's a high chance it's going to impact its pattern performance, its gain, its VSWR, and port isolation. Of course, it's going to depend where that object is relative to the antenna and where that antenna radiates. So if it's directly behind the antenna, it's probably not going to do much to it unless it's an omni. But if you have something directly above or directly below or on top, then you might see a bigger impact. Now, the next region is your near field region. So there's power stored here. You can actually put things in this region, but you're still going to impact the patterns to a minor degree. And then your far field region, where you can do anything in the far field, and it should not impact the performance of the antenna by itself. Now here I'm just showing for different frequencies. So yellow is 0.9 gigahertz and all the way up to 5.8 and red. What is where is the near field zone radius for a certain size of antenna? So we can see here that, sorry, I'm just going to look at my time, got time. We can see here that for a 5.8 gigahertz antenna, a 2-foot dish, you should have the near field zone about 5 feet. But as you decrease in frequency, the near field zone gets closer. Now you might think, well, that's a little weird, because at the same time, the free space path loss, we can see that as you go down in frequency. So here's free space path loss for different sizes and frequencies. That at 5.8, you get 50 dB of path loss. And then when you go up to lower frequencies, it's much less, it's 35. So that kind of tells you there's a trade-off between, you got to find the optimal distance where the path loss is maximum, but at the same time, you're still outside the near field zone for that antenna. So just a general guideline I'd like to say is you should space at least 3 feet apart, minimum. 6 feet is standard, more is always better. For omnis, I would try to space them vertically, and the reason I say that is an omni has a pattern that radiates equally in all directions. It's got this donut-shaped pattern, right? You want to put that other antenna that you're co-locating, right at the null of the donut. So imagine a donut, it's got the hole in the middle. You want to put the antenna that you want to put right by it, right on top in that donut hole in order to minimize the coupling between the two. And avoid impacting each other's patterns. So parabolics can actually be spaced fairly close together because they're so highly directive that they don't have much side lobes that you have to worry about talking between the two. Now, if you ever want to kind of back of the hand calculate how much interference do I expect to see between two antennas, you can kind of look at the two patterns of the antennas, where you space them apart, and so you look at the angles, and then you add in your free space path loss due to the distance. So here I have an antenna that's, let's say I have one that's at 60 degrees here, and if I go zoom in with my brain here, so you have two antennas that are angled 60 degrees, or separated such that their angle is 60 degrees. So you read the pattern here, and it says, oh, I should be at minus 6 dB, so that's how much isolation you get from just this antenna. And let's say you have two of the exact same antennas, so it's minus 6. And then you add it again, minus 6, minus 12. And then, so you have 12 dB of isolation just from patterns. Now you go look at the separation. Now, if I have 5 feet of separation at 5.8 gigahertz, I have 50 dB of isolation. So now you're at about 62 dB of isolation total, just from 5 feet of separation and two antennas where you space them such that the angle between them is 60 degrees. And then you go look at your, how your transmit power, your receive strength, and you say, okay, am I going to interfere with each other at all? And do I even care because I'm on different channels too? That's another question you need to ask yourself. So, it's not something I could briefly touch on. Every antenna is a little bit different. Bigger antennas need more spacing. That makes sense? This is kind of the key things I want to just mention is at least 3 feet, 6 feet is standard. Bigger antennas need more spacing. Omnis space vertically, parabolics can be closer. But there is a lot going on that you need to adjust for. Now, I forgot about this slide. This is our best practices for install. One of the kind of main things that we tell our clients is try your best to use a link planning tool, whether it's any of these I mentioned here, or whatever you want. I mean, there's free versions too of different softwares. And the reason we do this is we want to get an understanding of how much signal strength we should expect. It also gives you a good idea of where I should be tilting the antenna. It can get you the down tilt you need for it, and also the azimuth tilt. And you go use that, and now you take that when you're in the field, and you can help use that to align your antenna. So when you're actually in the field, first thing I would do is align your azimuth. So you can use GPS and waypoints or a gun scope. Try to avoid compasses because just due to the iron in these towers can really throw them off. So you have to be very careful using a compass. I like to use, or we suggest to use GPS and waypoints most of all, but get directly behind that antenna when you're doing it. So so you have a good sense of where it's pointing. Now, for elevation, use a digital level and place it on the flattest surface that you can find. Now, a caveat here is on a sector antenna, don't place it on the top, place it on the back surface. And the reason is these top caps on the radome, they can be a little bit uneven. It might be only 1 degree, but that's still a very significant impact on your down tilt, especially if you only have a 4 or 5 degree elevation beam width. So we say place them right here on the back. This surface right here is the most stable and also the most accurate place to put them. And then that's how you set your down tilt. So that's for these types of antennas. One thing you should always be careful when you're setting up a parabolic antenna is you got to make sure you don't lock onto the side lobes. These arrows are a little misaligned, but you always have your main beam. It comes down your pattern, and then you get your first side lobe. Maybe you get a second or third. But a lot of the time we see people locking on, not a lot, maybe a handful of times, see people locking on these side lobe levels. And you're going to notice it if you see a signal strength is 10 to 15 dB down. You're going to be wondering what's going on, and just go back to it and align it maybe to the left or right or up and down just a few, a hair, and you'll be able to increase your signal strength and kind of get back on track. Now, a number of different alignment tools. Some of them are more expensive than others. I'll just provide the names down here, but they're so far my research is the reviews on all of them are great. Now, radio combinations, let's just briefly talk about this. So this is our 8-port sector. So it's 4 ports in each band, 4 port at 3 gig and 4 ports at 5 gig. And here we kind of tailored it for using it with LTE equipment. Not to say you can only use it with LTE, but the reason we combined a 65 degree at 3 gig with a 90 degree at 5 gig, because you want to avoid noise. If we did 490 degrees at 3 gig, you end up getting a little bit of noise, and you can't do channel reuse as easily. So that's why we go to the 65 degree scenario. And so I'm showing here that the different radio combinations that are available with these sectors. So you could do a lot, 2 ubiquities, 2 cambium, 2 450s. You could even do a 3000 with a Mimosa A5C at the 5 gig, and at 3 gig you can use some BiSol equipment, Nokia or Ubiquiti or Telrad. And it just gives you a lot of versatility for using different radio combinations with one antenna. Also, the benefits of this is you can reduce your tower loading and rental costs if you are renting it, and minimize your install time. You can get all this set up on the ground for the most part, and you can go and just end up mounting this on the tower after you have everything on the ground ready to go. So here we do the same with 2 gig and 3 gig. I'm not going to run through it. It's very, very similar. Everything's pretty much the same except frequency changes at the low band. Then 2 gig and 5 gig. So you can see we have all these different combinations of the dual band. We also have so these are the slant versions, sorry. We have a 2HV, 5HV X8, and that's been going very well, actually, that product. So here's just another cool product we released, cables with boots. So these little boots here, they help improve the weather protection of the cable. They don't eliminate the need for taping, but they drastically do reduce it. And we recommend not to use mastic tape with these, but to use just black electrical tape instead, because it'll adhere a little bit better to the rubber. But these are excited. We have them of all different types of lengths, and end mail and RPSMA to end mail. This is a cool product we just released this year. It's a 4-port Omni that's used with the Cambium EPMP 3000. So this is an Omni that only works with this radio. We had to change the part number just to signify it only works with this radio. And really, it does some fancy things on the inside in order to take these bidirectional patterns and turn it into a nice omnidirectional pattern. So this is great if you want to provide coverage, for micropop deployments in small areas. I'll show you the example actually right now. Here, actually, before I get to that, one thing I like to note is that the top of the radio and the ports are protected from the elements using this aluminum cover. So it does protect you, from birds getting in there or whatever, rodents and messing with your cables. I hear that vultures like to pick at cables sometimes. So that does avoid that from happening. So here's from our field test. You can see the adapter. The hood is not on this unit here. But this is from the beta testing we did, and this client, he has a very affluent region of, some very wealthy clients that he's trying to serve, and he has some architectural guidelines, so he had to mount this Omni really low and paint it with this camel color to hide it as much as he can. By the way, I don't recommend mounting an 11 gig dish. I think this is 11 gig this low to the ground. It might be 5 gig, but you're going to run into some troubles. Obviously, it's working for him, but this is something difficult to do. But he's able to get 30 to 50 megabits per second, and then the added benefit is that MU-MIMO is working on this Omni. So that's one of the things we spent a long time designing, is making sure that multi-user MIMO works. So MU-MIMO is activating in the evening time, helping him get his additional bandwidth in order to serve these customers to high speeds. I mean, $5 million homes, you want them to make sure they have a reliable connection and the fastest possible. Here's the Omni that everyone got confused with. So this is another 4-port Omni. It's a 5 gig 4-port Omni that it's not the same style as before. It's actually two 2-port Omnis that are stacked vertically in the same casing. And this Omni, you can use it with any radio you want, or 2 radios, or two by two radios. And it just acts as a traditional Omni to just make sure that you have different channels on each port, on each of the 2 ports, pairs of ports. Otherwise, you're going to start interfering with each other. But you have 2 channels. Let's see, one's at Uni 1 and one's at Uni 3. This is going to be just like doubling your throughput with just 1 antenna. And of course, either 2 radios or 1 4x4 radio. Here's our ProLine parabolic antenna. So we have at 11 gig. So we've released some 11 gig dishes. These should all be in stock now. I think the 3-foot Mimosa isn't, but this is for the Ubiquity 11FX and the Mimosa B11. And then these are I don't want to go through everything, but just excellent antennas and well constructed. Fastest time to the tower because we pretty much pre-assemble everything in the box for you, or the crate for the 3-foots. And then here's our 5 gig dishes. So I think I'm pretty much done. Here's our latest adapter release for the Ubiquity ISOstation 5AC. And then here's our ProLine sector update. But I think that's pretty much it for me. We're releasing some 900 gear, so to help target certain markets that only need 1 port. So we have these 2 antennas here, and then also some unlicensed Omni single ports for CPEs. So email us if you're interested in learning a little bit more about these products. But these ones are actually available now, but these ones are not, the 5 gig ones and 2.4. But thanks everyone for joining my talk, and I really appreciate the time talking with you guys. So thanks very much.
Really good information, Justin. Very, very good. So we got a couple of questions here, and I can read them out if you'd like.
No, I got it here.
You got them? Okay, yeah, I'll let you carry on.
Okay, so James, is DBM more accurate than DBI? So DBM is relative to actual power transmitted. So I wouldn't say one's more accurate than the other. DBI is relative to isotropic, but where DBM is relative to a milliwatt of power. So I think DBM is more realistic because that's what you see in the field. You're transmitting 1 milliwatt of power, and you can actually see how much power am I going to receive based off of that transmission of that power. Where DBI is power agnostic. It could be referenced to anything. You can easily convert between the 2 by just adding how much power you put into it. So let's say you actually ended up putting 1 full watt of power on a 10 dBi radio, or 10 dBi antenna. You're actually going to radiate, so convert that 1 watt to dBm, so that's 30 dBm. And then you add that to your gain of your antenna, so plus 10 dBi. So you're actually going to be radiating 40 dBm of power out of that antenna. So that's kind of where we see, that's kind of what I think about when the difference between DBI and DBM. DBI is just for the antenna itself. DBM is actually what you're going to be using in your link budget calculation. So James, I hope that helped you out. Dave, so why did we use 716 DIN connectors? That was I'm going to just say a mistake on my part and some of the previous managers, in which we thought the industry was going for the LTE sectors to these 716 DINs because they are more robust at ensuring you have a good connection and avoid PIM issues. N-type connectors are notorious for having PIM issues, especially because the PIM is very dependent on how much you torque and tighten them. So there's an ideal torque setting you need to give to it in order to avoid PIM issues. So we wanted to kind of avoid that for our customer base and went to the 7/16 DINs where you can tighten them as much as you can by hand. You don't have to really worry about it because you're guaranteed that PIM value of, let's say, 152 dBm. But what we neglected to think about is how much it costs and the lack of 7/16 DIN connectors and cables on the market. So after we kind of learned that and we had the product out, we started getting inquiries from some of our customers on why we're doing this and can you source cables for us. And we ended up sourcing some cables in the short term, and we've resolved that issue. But we ended up end-of-lifing, I believe, those 7/16 DIN connectors. The only ones we have now are just ones that we have left in stock. I don't think we're going to be remaking any more of those ones unless we have specific customer requests. Now, it's not a big of a deal because they've released N-type connectors which have low PIM characteristics in them. So that's what we've been using now for our LTE equipment and actually a lot of our newer gear too. So that's kind of the reason why we went to 7/16 DINs. It was definitely a story, but something we learned on and corrected. Douglas, yeah, we do have plans for, so Douglas' questions was if we have plans for a 2.4 or 5.8 gigahertz dual pole Omni. I do have plans to do that. We want to do it right though. There are some already on the market. Alcom, our sister brand, actually carries a large number of them for different gain sizes, but we want to do something that differentiates ourselves. So we're spending a little time instead of just blindly doing what's, a Me Too product. We want to spend a little time to make sure we do something that's innovative and useful. But if you're looking for something like that, that there are some on the market right now. Maybe not in the gains you require. So if you want, follow up with us, and we can kind of get we say voice of the customer and understand what specs you want to see from a dual polarity Omni. And I don't know why I completely forgot we do have a dual pole Omni. We have too many products, I think, sometimes. We do have one that's dual pole, 2 gig, 5 gig, HV, both polarizations, and it's about a 10 dBi. Man, that's I'm sorry that I blanked on that one. So that one's available. It's non-slant. Yeah, you got it. It's
all right.
Horizontal vertical. Yeah.
Okay, I think that's it. If there's any last-minute questions, comments, feel free to type them in. We'll try to wrap up here quickly. So that being said, let's get to our skill testing question. So I'll give everybody just a moment to open the chat window. All right, here we go. So Justin went over 4 major differences between sector antennas and horn antennas. Name 3 of them. I'll give everybody a moment to plug their answers in. Just bear with us here. We just got to collect our we got to collect the results. We got all kinds of chats coming in here. All right, James, one of our question askers. You are the lucky winner. So, James, we will be in touch with you to get you that gift card a little later today. That being said, thank you everybody for attending. We really appreciate your time as always. If you have any questions, comments, anything comes up, you want a copy of the recording, get in contact with your sales rep here at MBSI WAV or sales@mbsiwave.com. MBSI WAV, we will be conducting more of these webinars as we always do. We'll be sure to keep all you folks up to date on what we're going to be talking about next. Just a bug in the air. We are working on a podcast series as well, which we should be seeing some of those episodes roll out here this summer. So keep an eye out for that. Again, any other questions, comments, feel free to reach out. Thanks again for attending. Stay safe, stay healthy, and we will catch you all later. Thanks for attending. Bye-bye.